If you have ever wondered what on earth is ARP, and you're curious about its internal workings, then you have come to the right place. We will break down the protocol, consider how it can be hacked, and whether you can defend against it. ARP stands for Address Resolution Protocol, and it is being used constantly in the background by our routers and switches and other devices. IP version 4 largely relies on this protocol because IP packets are useless unless you know what hardware address to send them to when they get encapsulated in the Ethernet frame. Also, if the device has multiple interfaces, it needs to know which interface it should use for transmission. This is why every Ethernet device holds an ARP table that consists of MAC and IP address pairs, along with the associated physical interfaces. When a device has to reach a particular IP address, it can just look it up in its ARP table. You could view this table on your computer if you wanted to. On Linux, you would just enter the command ARP into the terminal. Similarly, on RouterOS, you can view it by going to the IP ARP section and issuing print. As you can see, my table here only has a couple of entries. This is because the table is built as your device exchanges ARP messages with other devices, and furthermore, the entries are only held in RAM, so a reboot will wipe them. The only permanent ones are those that have been added manually. Manual entries are usually added for security purposes. Let's delve deeper into how the protocol works, and everything will become more apparent, including how ARP is vulnerable to attacks. The protocol is sometimes considered to work on the data link layer, but since the ARP packets get encapsulated in an Ethernet frame themselves, technically it is no longer layer 2. And it is not quite layer 3 either, in the sense that the IP layer, which itself is a layer 3 protocol, depends on it. So ARP could be considered as a layer 2.5 protocol, but many sources place it into either layer 2 or layer 3. If we have a simple local area network where there are several devices connected to a switch, then the basic functionality looks like this. Host A needs to contact host B using its IP address, but it does not know its MAC address, so it prepares an ARP request, also known as an ARP probe, that basically says who has this IP address X, and it then sends it with a broadcast MAC destination address to the switch, which in turn broadcasts it further to all the connected devices. Now, here we are putting our trust into this network, because we are expecting that all those devices will read the ARP contents and stay silent apart from host B, who will respond with what is called an ARP reply. This reply should be saying IPX is at MAC Y. And instead of being another broadcast message, typically it is a unicast message intended only for host A. The ARP packets are very small, and the contents are not as intimidating as they may first appear. The first 6 bytes are almost always going to be the same. The first 2 indicate hardware type, 3 zeros and a 1 is for Ethernet. Then you have 2 bytes for the protocol type, which is going to be 0800 for IP version 4. After that, you have the hardware and IP address lengths, which are always 6 and 4. The next 2 bytes can only contain 2 values. If it is a 1, it indicates that this is an ARP request, and if it is a 2, it is a reply. And then we have the actual unique payload after that, the sender's MAC, sender's IP, target MAC, and target IP. Let's have a look at this working between 2 routers. I've opened 2 terminals to router 1 and 1 to router 2. There are IP addresses added statically, but the ARP tables are empty. They are about to get populated, so I will start a sniffer on router 1 and issue the IP ARP print follow command so that we can observe ARP in action. Now I will try to ping router 2 from router 1. ARP request and reply packets got exchanged immediately, and the pings were successful. But then a second ARP exchange took place, even though IP communication was already working. So what is happening? Here is what this would look like in Wireshark if we saved the sniffed data. Router 1 sends the request asking who has this IP. The second router responds, and ping is immediately taking place without any issues. But then router 2 asks where to find router 1. how could it respond to the pings if it didn't know where to find router 1? This is a typical behavior of Ethernet devices, where when one device has no knowledge of the other and it receives an ARP request, it will use the data from the request not only to prepare the reply, but will also update its own ARP table, and only moments later will it try to verify the new ARP entry by sending an ARP request of its own. Pretty smart. We can copy the ARP request frame in hex and break it down by its components. It begins with the typical Ethernet header, MAC addresses and an ether type indicating that the payload is ARP. Then we see the part that is almost always the same, followed by addresses. The IP addresses look a little strange as they are displayed in hexadecimal and not decimal format. And the target MAC address is set to all zeros as that is what we're trying to query. An interesting nuance is that if we copy the reply hex stream, we can see that it is heading to the source MAC address of the request instead of the broadcast MAC. But what exactly are all these zeros at the end? Well, that is just Ethernet padding that can be ignored. When a device prepares a frame containing ARP, it ends up only 42 bytes in size, which is under the 64-byte minimum Ethernet frame size. And once the frame is actually leaving the device, the driver will still add a 4-byte footer, and whatever is the difference between the total frame size and the 64-byte minimum will be inserted as padding between the ARP packet and the footer. This difference happens to be about 18 bytes for ARP or 36 zeros. Now that we understand ARP at such depth, we can have a look at how to do gratuitous ARP from RouterOS. Gratuitous ARP can be sent either in the form of a request or a reply, but the purpose is the same. It uses a broadcast message to announce your IP and MAC address pair to the network before anyone has asked for it. This can be useful to prevent address conflicts and in some situations where you might want to reuse the same IP on multiple devices or interfaces. For example, a setup where one device going down is immediately replaced by another one. Not all devices listen for these types of announcements, and not all devices are capable of sending them. In RouterOS, you could make these through some scripting and the use of traffic generators inject feature. It is probably the most powerful tool in RouterOS as it allows you to forge any frame that you like. For gratuitous ARP, you can see an example on our help page. It is just like one of the hex streams we copied. The target IP is the same as the source IP, and the target MAC is all Fs. This tells every recipient that they should add the sender's IP MAC pair to their ARP table. Another thing that you might notice is that there are the 36 zeros at the end of the data, the padding that we just talked about. Technically, it is not necessary to include it in the data as it should be added automatically, but it doesn't hurt it being there. If somebody wished to attack a network using ARP, they probably would not use RouterOS to forge their frames, as it would be simpler to do the whole attack from some laptop or other Linux device. But if they have physical access to your network, they can do what is called ARP spoofing. In the context of the network with the 4 hosts, host C could use ARP to trick host A and host B into believing that they have to communicate through them, creating a man-in-the-middle situation. Or they could just do a denial of service, flooding everyone with ARP packets. That is why someone might want to disable ARP and only rely on statically created ARP table entries. As you can see, I have one dynamically added ARP entry for interface Ether 1 on this router. If we now go to the interface Ethernet section, there we can see the ARP status for all our physical ports. Ether 1 is entry 0, and we can change the ARP status to whatever we like with the set command. Besides enabled and disabled, there are 3 more entries that I will cover in another video. Okay, so I will disable ARP for Ether 1. And now, when I go back to my ARP table, there is nothing there and no IP communication will be possible from Ether 1. To allow a specific MAC IP combination, I can add a manual entry using the MAC address from before. But that unfortunately is not enough. We also have to add a manual entry on router 1 because eventually its old ARP entry is going to get discarded and router 2 will not reply to new requests. With both static entries, this IP connection works. But let's say one of the MAC addresses changed. I'm just going to swap out one digit on the router that we were contacting. And if I try to ping it again, it no longer works, because the MAC address no longer matches our ARP table. So that is how you can do manual ARP. It prevents the worst effects of ARP spoofing, but of course layer 2 is still very vulnerable to all sorts of attacks. In RouterOS, there are other powerful tools like bridge filters and switch filter rules that can help you with that. Speaking of bridges, if you have added your Ethernet ports to a bridge, then besides disabling ARP on your physical ports, you will have to also disable it on the bridge interface, similarly to how we did it on the interface Ethernet section. Let me show you what happens if we don't. I've added our interface with the disabled ARP to this bridge. Now if I ping the IP we could not ping a moment ago, it succeeds this time, and as you can see, another ARP entry is added with the altered MAC and the bridge as the interface. This is because the bridge interface itself is like another real interface that shares the same broadcast domain with all its member ports. So the broadcast ARP messages will still be received by the bridge even if the ports ignore them. If you enjoyed this video and you want to learn about the other ARP options we have on RouterOS, make sure to like and subscribe because that and lots of other interesting and educational content will get posted on this channel. See you next time.